In this lecture, we are going to examine the use of the force method for analyzing statically indeterminate trusses. Lecture Essay 24 provides background content for this lecture. Please review it before proceeding with this one. Here, I am going to assume you are familiar with the basic ideas behind the force method. Indeterminacy in trusses could be external or internal. Let's consider each case separately. Here is an externally indeterminate truss. How do we know it's indeterminate? The truss has 5 member forces and 4 support reactions, for a total of 9 unknown forces. Yet we can write only 8 joint equilibrium equations, 2 equations per joint. Since the number of unknown forces is greater than the number of joint equilibrium equations, the truss is considered indeterminate. Further, since the difference between these two numbers is 1, the degree of indeterminacy of the truss is also 1. And how do we know the indeterminacy is external? The truss has 4 support reactions. This means in order to calculate them without calculating any of the member forces, we need 4 equilibrium equations. But, using the free body diagram of the entire truss, we can write only 3 equilibrium equations. This means we do not have enough equations to directly determine the reactions. This makes the truss externally indeterminate. Therefore, to analyze the truss using the force method, we need to select one of the support reactions as a redundant force. I am going to pick the horizontal reaction at B as the redundant force. Let's refer to it as Bx. By removing Bx from the truss, we permit joint B to displace horizontally like this. Let's call this displacement delta x. Now, we place a unit load in the direction of Bx at joint B, causing the truss to displace like this. We refer to this displacement as lowercase delta x. Then, we can write the compatibility equation as, since these are displacements in a statically determinate truss, we can calculate them using, say, the virtual work method. When calculated, delta x comes out to be PL over EA, and delta x equals L over EA. So, Bx can be easily calculated using this equation. Bx equals P. Now that we know the magnitude of the redundant force, we can analyze the truss using, say, the method of joints to determine the remaining member forces and support reactions. Here is another example. This truss is also indeterminate externally. The truss, having 4 support reactions, is indeterminate to the first degree. So we are going to make one of the support reactions the redundant force. Here is the free body diagram of the structure. Let's pick the roller reaction at D as the redundant force. We note that in the original truss, the horizontal displacement at D is 0. But, when the redundant force, labeled dx, is removed, the joint is going to move horizontally by some amount. Let's denote this displacement as delta x. Then, the redundant force dx is what we need to push joint D back into place. In order to find this force, we need to calculate 2 displacements. Delta x, the horizontal displacement at joint D under the applied load, and delta x, the horizontal displacement at D due to a unit load applied in the direction of dx. Then, we can write the compatibility equation as delta x equals dx times delta x. Knowing the 2 displacements, we can easily solve the equation for the unknown force. Let's use the virtual work method to calculate the 2 displacements. See Lecture Essay 21 for an overview of the method. To calculate delta x, we first need to analyze the truss under the applied load. The analysis yields the following member forces. We then calculate each member elongation using equation where F is the member force, L is the length of the member, A is a cross-sectional area of the member, and E is the member's modulus of elasticity. Here are the elongations. Now, we place a virtual unit load in the direction of the target displacement and analyze the truss again. This time, we get the following member forces. According to the virtual work method, we can write where delta I is elongation of member I due to the real load, and F star I is axial force in the member due to the virtual load. Then, delta X can be written as we follow the same procedure to calculate delta X. First, we analyze the truss under a unit load placed at D in the direction of the displacement. Here are the member forces. Then, we determine member elongations using equation. Here are the elongations. The analysis of the truss under a virtual unit load at D gives us the same member forces. So, for virtual member forces we have, therefore, delta X can be written as or delta X equals 17 over EA. We can now write the compatibility equation as, solving the equation for the redundant force, we get dx equals 10.9 kilonewtons. Here is the free body diagram of the truss with the known redundant force. We can now use the equilibrium equations to calculate the remaining support reactions, or use the method of joints to analyze the entire truss. Let's analyze another truss, one that is internally indeterminate. The degree of indeterminacy of this truss is 1, so we need to make one of the member forces redundant. Say, we pick member AD for this purpose. To make the force in the member a redundant force, we assume the member is cut, thereby taking away its ability to carry an axial force. This, in effect, turns the truss into a statically determinate one. Now what happens if we place the applied load on the truss? It is going to deform, and a gap develops at the cut point. Let's denote the length of the gap as delta. Since the revised truss is statically determinate, we can easily calculate delta using the virtual work method. For our truss, when calculated using the virtual work method, delta equals. Now, we apply a unit axial force to the cut member to reduce the opening caused by cutting the member, like this. And we measure the resulting axial displacement. Let's refer to this displacement as delta. Delta can also be calculated using the virtual work method. Here, delta is. We can now write the compatibility equation as or so the redundant force equals P over square root of 2. Once the redundant force is computed, we can determine the remaining member forces using the method of joints. Before we wrap up this lecture, let's solve another example problem. Here is an internally indeterminate truss having a degree of indeterminacy of 1. Let's analyze it using the force method. We can pick the force in member BC as the redundant force. After cutting the member, the truss is going to deform like this. We need to calculate delta. To do so using the virtual work method, we need to analyze the truss. This can be done easily since the truss is statically determinate. Now, we calculate member axial deformations. They are Next, we place a pair of virtual unit loads in the direction of displacement at the cut point in member AD, like this. Then, we analyze the truss to determine member forces. They are According to the virtual work method, delta can be expressed as where F star I is the force in member I in this diagram, and delta I is elongation of member I we have computed previously. So delta is (1264) over EA. Now we need to compute delta. This is displacement due to a unit force applied at member AD at the cut point opposite in direction to the displacement caused by the real applied load. This pair of forces induces the following member forces. We can then write member elongations as We then place a pair of virtual unit forces in the direction of delta. This gives us the exact diagrams and forces as shown here. So we can write delta as This gives us delta equals 130 over EA. Consequently, the compatibility equation can be written as Knowing the two displacements, we can easily solve the equation for the unknown force. We can now use the method of joints to calculate the remaining unknown forces. Here are a couple of exercise problems.